Good morning, everyone. What we're going to do today is related to continuous bases and continuous variables because they are quite important for quantum mechanics. And so far, our emphasis has been on discrete basis sets. So this is the main topic of this clip. Okay, so if we're dealing with continuous variables, the first question that we will ask is what changes with regard to discrete variables. And we have seen throughout our lives that when you have continuous variables, you can change sums, or typically what happens is sums become integrals and Kronecker delta functions become Dirac delta functions. So we're going to see how this works in practice. And to be more specific then, we'll consider a continuous basis set. And here you can see you have these cats omega alpha. They are assumed to be orthonormal, linearly independent, and to form a spanning set, which means they are a basis. And this alpha is a parameter that varies continuously. So it's a continuously varying parameter. Then we can define for this basis set an orthonormalization relation. So we can say that the inner product of a vector omega alpha with a vector omega alpha dash is equal to the Dirac delta function of alpha minus alpha dash. And just to remember, when you had a discrete basis, the orthonormalization relation was defined by taking a state vector psi j and psi I, so bra psi j, ket psi I, and this was the Kronecker delta. So you can see actually this change that I mentioned at the beginning of the clip taking place. Now, we can also define a closure relation. We can also say that the integral over alpha of this operator here, where you have ket omega alpha bra omega alpha, is equal to the identity operator. Again, for discrete basis sets, you would have something like a sum giving you a similar relation. And we can use this closure relation to represent cats and bras. So we can insert this here when you have an arbitrary state vector psi. We can write this as identity operator applied to psi. And this is going to give us this expression. So you can see that psi is now written in terms of this spanning set using this integral. And we can do the same for cats, and then we can do the same for bras. So remembering that a bra is a vector in the dual space, or for a function now in the state space, you can write this in terms of bra up, and using the identity operator, we get a similar expression. With the difference now that this bra is written in terms of these vectors in the spanning set. Now, fair enough. How about operators? Because we have seen bras, we have seen cats, and we need to talk about operators. So what is going to happen to them? We can pretty much do the same as before. So we can insert now two identity operators. So if we have an arbitrary operator A, it can be written as identity operator A, identity operator, one applied from the left, the other applied to the right. And you find, when you do the math, this expression. So basically what you have to do is you can just write, in this case, A is equal to integral d alpha omega alpha omega alpha, and then here to the right you have integral d alpha dash omega alpha dash omega alpha dash. So basically I'm just applying the identity operator. So here this is equal to identity operator, this is equal to identity operator. And then when you do this, you end up with g alpha dash omega alpha a omega alpha dash, and then here this corresponding bra omega alpha dash. Okay, so it's pretty much straightforward to see how they are going to work. Now, with regard to expectation values, you do pretty much the same. So we can discuss in detail, but the procedure is the same. Just get one here, and you'll find this expression. And this is important because sometimes you need to use a basis to solve a specific problem. And we are going to see two very important examples right now. But what matters to me at the moment is that you can write this using the spanning set, which is pretty much the same here. You see, this is familiar. I'm doing this quite general, but once I've got through a specific example, you see how it works. And we can also define here eigenvalues of A. So if you apply the operator A to a specific basis vector in this continuous basis, which here I called it differently, alpha nu, then you get alpha nu. So again, this varies. So let's have a look. And one important thing here is that all these expressions, they can be generalized because sometimes you don't have only a discrete basis set. Sometimes you are dealing with a problem in which you have to write your state space considering a discrete part and a continuous part. So, for instance, here, how do you do it? One thing that you would have to know then is what is discrete, what is continuous, and in this case, your closure relation would be given by this expression here. And what you can see is that here you have a discrete part of your spanning set, and here you have a continuous part. Question, what are the situations in which you have to do this or you must be faced in your life? So examples, when you're studying, for instance, atomic physics, and you're looking at a spectrum, sometimes you have a discrete part like bound states, and the continuum. So you would have a potential and you have something that is bound, but once you're here, you have like a continuum. You can also think, because I know some of you are doing condensed method, for instance, if you're looking at a condensed method system, what are the conduction bands, the valence bands? They are regions that are pretty much continuous. So you have regions where your spectrum of your system is going to be continuous. But if you put, for instance, impurities like this one here, you have acceptors, donors, etc., you're going to have bound states. So you have a bound region and a continuum region. So in this case, your closure relation would be given by that expression here above, and our basis vectors would be the following. In the discrete part, you would have psi I, where I is an index that is varying discretely. So varies discretely. Say if you have 10 bound states, then these energies are going to vary discretely. And in the continual part, you have this set psi nu, where nu is a parameter that is varying continuously. And what you can see is, for instance, here, you can clearly see you have this sum over this discrete part of the spectrum, plus this integral, which ranges from nu1 to nu2, and this is a continuous region. For instance, this would be over whatever you can get in your conduction band if you're dealing with a solid. And here, the other part would be related to your bound states. And this is important because you need to know how to generalize, and this is will be pretty much dictated by the problem that you're looking at. So you're not only going to have continuous sometimes problem or discrete type of problem. And if you would like to expand your wave function, in this type of basis, you would again, here, you insert your identity operator, right? But you have to be careful now, because your identity operator is given by this closure relation. So you have this discrete part and this continuous part. And when you insert this, then you get this sum over this part of your basis. And then you have this integral going from nu1 to nu2 over nu, considering then the continuous part of your basis. And this is something that is really, really important to take into consideration.